Hi-oh, here we are again. I'm going to talk about fields, electric shielding, electric potential, and electric potential energy. Let's start off with electric fields. Just like you have a gravitational field, basically an invisible force around something that is caused by gravity, well, we have an invisible field or force around an electric charge. It behaves very similar, only gravity is attractive, and we know that electric charges can be both attractive or repulsive. And we also learned from Coulomb's law that the electric field is much, much stronger than the gravitational field. So how do we determine this? Well, some time ago, it was determined that everyone should use a positive test charge. Basically, we take a positive charge and we test the field. If the positive charge gets pushed away, we know the other charge that we're bringing it near must be positive. So we draw this with arrows pointing away from that positive charge, the charge that we're testing. These arrows, of course, if you might remember, are vectors. They talk about a force and direction. So if we bring, likewise, if we bring a positive charge to test the field near a negatively charged object, it's going to get pulled in. And so we draw our field with arrows pointed in. They're attracted. And it should stand to reason the closer you are to that object, those two charges are together, the stronger the attraction or repulsion. And so when you look at the field lines, you find that the closer they are together, the stronger the field. Some examples. Again, a positive charge has the field lines going away, and a negative charge has the field lines going towards. Electric shielding we need to talk about. This plane and passenger, they're completely safe. It turns out the electrons, what they want to do is they want to arrange themselves so that they're as far away from each other as possible. So they tend to put themselves on the outside of objects rather than the inside because they'd be farther away, and they'll distribute themselves so their field lines cancel. So the field line inside, the field inside any hollow metal object is zero. This is why these passengers are safe within this plane. This is why your car is the safest place in an electrical storm. This is why we encase electrical components inside some type of metal container, because it protects them from getting fried. Speaking of which, if we watch this lightning stroke, this is the part you don't normally see, and when it makes connection with the ground, we get the return stroke. Contrary to popular belief, most lightning goes from the ground up, at least the part that you see. So that tells us something. That tells us that lightning can strike from cloud to ground, ground to cloud. But if you look in this animation, you can see that lightning is also striking back within the cloud itself. So lightning goes from cloud to cloud, intercloud lightning. Finally, we need to talk about these two similar sounding ideas, something called electric potential energy and electric potential. You have to realize the first word is really an adjective, electric. We're talking about electric things rather than gravitational. So if you really focus on the remaining part, it becomes a lot easier. So the first part is potential energy. We know this when we talked about gravity, gravitational potential energy. We know that as you moved stuff away from the earth, we stored that energy. We took that work and stored it in the form of potential energy. Look at that, potential energy. Well, electrical things are no different. In my animation, we have some positive charges. We're moving them away from the electric charge, from the negative electric charge. It takes work to do that. We're storing the work in the form of potential energy. And like gravitational things, we measure this in joules. However, something a little different, something we call the potential, the electric potential. You know this is voltage. We measure that, of course, in volts. Very simply, it's defined as the energy per charge. You can almost think of this as an average. How much energy per charge? We look in our picture here at the bottom. Notice these charges are the same distance, charge A and charge B. Each charge being the same distance from our other charged object has the same amount of work done to get it there. So the energy per charge is the same in both of these cases here. The potential is, so let's blow this up, make it a little bigger to see. So which charge has more potential energy? Well, B is very similar to lifting or pulling away more charges, lifting more bricks. So it took more energy, more work was done. So B, of course, has more stored. How about electric potential? The average is the same, right? The potential, which we measure in voltage, we use a V, is the electric potential, or the energy per amount of charge, and that's what they. So here it is as a review. Electric potential is the energy per charge. We measure it in volts. Potential energy, the electric potential energy, this one is due to Coulomb forces, not gravity. Depends on the location, right? As we move it farther or closer away, and of course we measure it in joules. To further the review, let's say we take two similarly charged objects. They move closer and closer to each other. So here's maybe a positive and another positive. We're going to move these closer. What do you think? The potential energy. Right, more work was done to do that. So the EPE increases. Why did it happen? Already said it. More work was done. What if I do 10 joules of work to pick up something in a gravitational field? We know that the brick has stored exactly 10 joules of energy. What if I do 10 joules of work to move a charge in an electric field? How much energy? Well, energy is conserved. We know we still have those 10 joules. So what is the electric potential if we have a 3 Coulomb charge, that's Q, and 6 joules of energy? That's the potential energy. Well, we know our formula, V equals EPE over Q, and of course the EPE was 6, the Q was 3, so we have 2 volts of potential. We can use that same formula and solve it for the energy itself, right? V equals EPE over Q. So here we say we have a 2 Coulomb charge right there, that's 2. And it has a potential, that's 12. The EPE is, the energy is 24 volts. There you go. I'm sorry, joules.